All right. Hello, everyone. Hope you doing well so far. Today, we're going to be having a 45-minute discussion with Assistant Professor Mayank Kejriwal, which, as was previously stated in the Google Calendar invitation, is an expert on artificial intelligence, currently at the University of Southern California. So he's going to be giving a discussion on artificial intelligence, especially given his context as our subject matter expert on INFER. So he might be able to give some insight that has been guiding that campaign on the website. This will be a discussion first that Mayank is giving, followed by a Q&A session. So if you do have any questions throughout, make sure to just put them into the chat, and then we'll be able to address those later on. All right, I can pass it over to you, Mayank, whenever you're ready.
All right. Yes. So thank you all for coming and for organizing this session. So let me just jump into the presentation. And I'm now in full screen. Is everything still good? All right, great. Okay, so so I am an academic in artificial intelligence, and I usually give a lot of talks on sort of what's good about AI or what's bad about AI. So when does it work, when does it not work, what are the new algorithms that we are working on, and so on. But today's talk will be a little bit different, and I think more relevant to the forecasting that we've been doing, as well as to the material that you have been exposed to so far. And that is really about the future of computing and why we need a future of computing to do the next generation of artificial intelligence, and why is that relevant for us? What does that do for our national security and geopolitics and so on? So I'll try to give you some very specific examples of why we need a future of computing, why it's so imperative now, and especially in the next 5 to 10 years, which really is now, because we need to build these things now in order to have them commercialized and usable in the next 5 to 10 years. And what are some exciting things on the horizon that could provide Western countries, including the US, with leadership, or help us maintain leadership in AI. So let me move on to just a little bit about me. So I hold joint appointments in the Department of Industrial and Systems Engineering, and also at the Information Sciences Institute. So this is kind of where most of my research is done. And we are primarily funded by the Department of Defense and DARPA, also IARPA. You may have heard about some of those. And also some National Science Foundation, National Institutes of Health. So across the institute, we have a range of funding. On the right-hand side, you see some of my own projects, many of which have been funded by DARPA or are being funded by DARPA. So two good examples would be common sense reasoning and building AI that can handle novelty in the real world. So these two are sort of moonshot problems that DARPA has been looking at, but other things like using AI to fight human trafficking, using AI for crisis response were also DARPA funded. And we've also done other projects on computational social science. We work with companies on applying AI for e-commerce and so on. So in general, I'm very involved in applied AI. So, but also involved in what we call artificial general intelligence. And so with that, let me move on to what that is. So the moonshot goal of AI really is, for many people, some do not say it openly, but more and more they are starting to say it openly, is that the real goal really is AGI, or artificial general intelligence. And the idea here is, even though there's some disagreement, it's one of those things where intuitively you want the AI to be able to do the range of tasks that a human can do at human level performance. So we don't just want an AI that is superhuman in chess, but can't do anything else. We don't just want an AI that is very good at face recognition, but can't do anything else. We want an AI that can take in a lot of different inputs at the same time, whether that's vision and speech and touch and all those things, and can also is capable of doing doing a lot of things. And this is in an aging society. And as productivity is plateauing, and with trends like the Great Resignation that was happening, sudden shifts in the labor force and so on, we really do need something that can really assist humans and be sort of change the workforce in a way, and also change national security. So we need the AI to be sufficiently broad and have human-like performance on everyday problems. And two examples that I tend to be very interested in is language understanding, which is of obvious importance, and another one a little bit esoteric and subtle is common sense reasoning. So I won't go too much into the common sense reasoning, but the language understanding hopefully is sort of very intuitive and clear. If we want to talk to the AI and have it talk back to us, we do need very good language understanding. So what's the possible roadmap? I mean, there's a lot of different researchers and research areas, and here's a figure I really like. It's from a non-academic, I think, but it kind of really shows you what we're gunning for. So there's ANI, which is artificial narrow intelligence. Everyone sort of thought that the Turing test would be the mark between the ANI and AGI, but this is now controversial because we have AI that is now able to beat the Turing test on a number of tasks. I'll show some examples, but it's not so clear that they actually are AGIs that are beating the Turing test. So it's kind of controversial whether the Turing test is the right test. Other tests are being proposed as well. But certainly, there is on the left-hand side, which is kind of my contribution to this figure, you do see that a lot of different things are needed to get all the way up to, artificial super intelligence, whatever that might be. But certainly to get to artificial general intelligence, we need AI to have understanding of causality. We need AI to have a theory of mind. Can the AI understand what my beliefs are and how I am looking at the world? And does it have an effective model of me? And that's kind of where the theory of mind comes in. Very important when you are talking to other agents and human beings and interpreting their actions and intent. Common sense, events, temporal understanding, contextual understanding, open world learning. Can it deal with novelty? This is useful for self-driving cars, for AI that encounters unusual, irregular situations that it may not have trained for, which happens a lot in the real world, happens a lot on the battlefield as well. So, we're not there yet. There are many problems to be solved. Now, I mentioned that, people used to be skeptical about, academics used to be skeptical about bringing up AGI. The reason was it used to be a very science fiction kind of thing, right? Like you would not talk to, but you would see, something like Star Trek, where you have the computer on the spaceship, and you would have, commander data and all of that. And, they were very sci-fi, right? I mean, no one really thought that something like that was even within remotely possible. Then, of course, what happened was that deep learning came along, and there are many critics and supporters of deep learning. It can divide people sometimes, but its success is hard to argue against. So, I am personally not a deep learning researcher, but I use a lot of deep learning, and I give credit where it's due, and it's very hard to argue against its success on a range of tasks. And over the last 10 years, deep learning really has been driving an AI boom. There was a recent New York Times article where they kind of acknowledge in the popular press that AI really is getting very good. It's not perfect. It's very far from perhaps where we would ideally want it to be. There are problems of bias. It can break sometimes when it shouldn't. But by and large, it really does work very well. And as the New York Times says, we're in a golden age of progress. And it's time to start taking its potential and risk seriously. So everyone is now taking this seriously. And it's very possible that in our lifetimes, we will see something like AGI. It could be as soon as 10, 20 years from now. It could be 50 years from now. It depends on how you define it. And here's some specifics. So, language understanding, for example, has really come very, very far. So there's a lot of information here, try not to read all of it. What you're seeing here on the left-hand side are a lot of language understanding benchmarks. These include question answering. You give the model a question, it's supposed to give you back an answer. A lot of times you give it choices and it has to select the choice. This is kind of like your SAT and your ACT and GRE exams, standardized testing. And notice how when they had first been published, and this is accuracy usually, how many questions did the model get right on a scale of 0 to 1? So you can convert this to a percentage by multiplying by 100. So when they first got released, which was not a long time ago, 5-10 years ago, the performance was like 50%, 60%, sorry. And the state of the art performance now is well over 80%. In some cases, they are even higher. This is maybe a few months dated. I think it might be even higher now. And it's approaching human performance. So, at least on this task, right, we are starting to see, on language understanding, that the models are approaching human performance. That doesn't mean that once they achieve that, it will get to AGI, because remember, they have to solve several problems at human performance to reach that. But this is very promising. You can see the rapid progress in here. And it's not just language. So impressive advances have been achieved in computer vision and generative models, sometimes to a scary extent. So what you're seeing on the right-hand side is what we call deepfakes, and it's eerie, right? I mean, you would not really be able to make out looking at the deepfake that it is a deepfake. You may have seen the press articles, where President Obama or Elon Musk or they have deepfakes generated on them. It looks eerily accurate. On the left-hand side, on the plus side, we have this model called DALL-E 2, which was just released to more than 1 million people by OpenAI. And everyone has been writing about this. My own student has access to this, so he's been playing with it like a child, I might add, but that's the joy of science a lot of times. But this was generated by the AI, given just a prompt, and the prompt was infinite joy. And this is just kind of a quirky picture, but it can generate anything. It can generate photography, it can generate abstract art, and if you're really interested, search for DALL-E 2 and you'll find many articles. So it's not just language. We're starting to see human-like performance in generative, creative tasks as well. But I will focus a little bit more on language, because that really is where I do a lot of my work, and I think it's easier to perhaps explain the need for the future of computing when we look at language. So language models, which are these neural networks that basically can solve these problems very effectively. And for a long time, they were quite small, small by comparison. So you look at 2017, 16, the models were 94 million parameter models. But very quickly, the BERT model, which is very famous, is integrated into the Google search engine by this point. It was really the model that kind of led to the first big leap. So in that chart I just showed you, where we went from 50% to 70, 80, 90%, the first big leap really came because of BERT. And BERT is a new kind of neural network. So this is a paper, and you can see here that it's these deep bidirectional transformers, which is a new kind of neural network that was proposed with BERT around that time. And since that time, it has exploded. So this chart stops at 2020, but we are already talking about billion parameter models. So why is this important? Because machine learning is really the optimization, finding the right value for parameters. And the more parameters you have, the more data you usually need, and the more time it takes, the more compute heavy it gets, the more energy intensive it gets to actually train the model. It's kind of like saying that a piece of equipment gets bigger, right? It requires more energy, or if it's doing more things, it requires more energy. It's kind of like that. The neural networks are getting bigger and bigger and bigger, so they require more energy and more computation and more memory and more resources to train effectively on bigger data sets. And they will continue to get even bigger. So the latest from Google research is this PaLM model, which is now scaling to 540 billion parameters. And on the other side of the, of our globe, China is investing very heavily in this through its big tech companies, but also nationally, where Baidu introduced a 260 billion parameter model in late 2021. Here again in the US, AI21 Studio released a 178 billion parameter model. GPT-3, which can write poetry and generate text, is a 175 billion parameter model. The day is not far, maybe less than a year, before we actually have models that are where it's commonplace, right? The big companies have models that are trillions of parameters. There's already talk of that. There is already some work along those lines of a trillion parameter models. So we really are talking exponential. So before, needless to say, I mean, we are starting to hit a wall when it comes to training these models. I mean, it takes millions of dollars to train these models. It is perhaps not surprising that when you look at all of these models, there are very few academic practitioners. I mean, the University of Washington is one, but it's not really a very big model. Most of the models are Microsoft, Facebook, Google, and so on. The reason is not that they have brilliant researchers. I mean, you're going to find them in all the top academic schools. The reason is that they can actually spend the money to train these models. And, typically the funding agency is not going to give you millions of dollars to train a model. So what happens is we have to rely on these companies to train these models. Then they make a version of the model available, and then we can download and customize them, what we call fine-tune them for specific problems that we are interested in at lower cost. But the models are getting so big that even fine-tuning, even customizing is getting expensive for anyone who is not within these companies. And Congress has taken note of AI generally as an emerging technology. They didn't call out language models here, but what they have said is that future national security of which artificial intelligence is one, is something that is very important. They are concerned that the Department of Defense is not, according to them, postured correctly to invest in the correct emerging technologies or play the role of co-developer. I mean, certainly the bigger companies have been contributing more to this than perhaps they have. And overlaying this is a competition with China. And here they mentioned some things which really, I think, when I try to create forecasting questions, I'm mindful of some of these, which are, we need, stronger, we need to predict, where we're going with this, with the National Research and Innovation Enterprise, the status of the workforce, the status of research, the health of the manufacturing and industrial base, infrastructure, and so on. So what I'm going to do now is, I do have some more slides, but I'm just going to take about 5 minutes to run quickly through what are some things on the horizon, but I won't go too deep into it, but I will point you to something you can search for if you want to learn more on those. But I do want to, now give you some options for what these future of computing architectures are, what's on the horizon. So, but I do want to emphasize that US geopolitical leadership in AI could very well depend on designing new effective computing architectures. By this point, I think we have leaders all across the world, whether it's China or the European Union or the US, where people know how to work with big neural networks. It seems like that is what the future of AI really is going to depend on. We have some new architectures, new software architectures, new neural networks, new paradigms on the software side of AI, the model side of AI. But that's kind of democratic. They get published in top peer-reviewed journals and conferences. Anyone can adapt and use them. But computing architecture, the hardware, is not that easy to research and build. And typically there is a geopolitical element in this, when you're building computing architectures. We're seeing that now, right? With the CHIPS Act and the semiconductor leadership and so on. So even with something as simple as semiconductors, it's not that easy. In principle, we all understand semiconductors who are in the field and how to build the chips. And it's not really a secret. But to actually set up the plants that will build all those chips and will optimize them is really not, something that anyone can just do tomorrow. So this is where there is a big part of the competitive advantage, as well as the geopolitical competitive advantage comes in, the hardware. So what do we use for high performance AI today? Well, there are the graphics processing units. This is kind of what these are available. You can buy them. They used to be used for gaming. That was really where they what they were first developed for. But now they are used for machine learning a lot. And more recently, Google has released these things called tensor processing units, which have kind of, are really very promising. And this is, technical, but the point here that I want to point to is that these TPU are evolving very quickly. The power is like halved between the V3 and V4, but the peak compute per chip is doubled. So the chips are improving and they are getting more power efficient, and that's good news. The question is, are they good enough? And in order to measure that, there is this benchmark suite called ML-Perf. This is a community-wide effort. We recently had a forecasting question on this as well. What they do is they really want to understand that how efficient, how much time do these different architectures take to solve some of these problems. These are very well understood problems in machine learning. They are benchmarks, and without, while meeting this minimum quality target. So the way that this works is, if you have a chip or a new architecture, and all of these companies tend to participate in these benchmarks, you would run the task. You have to get a minimum effectiveness, and then you would report what the time is that it took you to actually solve this task. And what ML-Perf is measuring, that are you taking less and less time? I think I don't remember if they have something on energy. I'm not sure that they do. It's kind of an open problem right now in the community, with some new papers coming out that how do we actually measure the carbon footprint of training a model and so on. So this is an active area of research. This model is only the first step. All it's saying is, are the chips getting faster while still meeting the quality target? And they encourage new companies and research labs, and it's very interesting. And we have a forecasting question on this with some references and so on. So hopefully this provides some context on why ML-Perf is important. And our US company is going to keep maintaining their lead on ML-Perf. It's also a question that is very important to the community. So this is what we're doing now, right? This is what's happening now, but we are starting to hit a wall as we get into the trillion parameter models. So what are some paradigms that are particularly relevant for AI? Well, I'll just go very quickly over them, but then I'll stop for questions, and I'm happy to come back because I know we should have 20 minutes for questions. So the most obvious one, and perhaps the one that you heard of, is the quantum computing, right? So quantum is important not just for AI, but also for cybersecurity and so on. Now, the thing that makes quantum computing so unique is that even a 50-qubit quantum computer, it turns out, if it's designed properly, a 50-qubit quantum computer could actually beat a classical supercomputer on some tasks. So, this is really not, 50 qubits is challenging to put together, but it's companies already starting to do it. And, China and the US are both heavily investing in this. In fact, there have been articles from Scientific American in the bottom and another article at the top where, we're really neck to neck in this. It's not so clear who's going to pull ahead. And this is one of those technologies where if you pull ahead, it's even small difference can suddenly open up entire possibilities that may not be available to your rivals. So this is a very important paradigm. Another one that is very exciting in a way is neuromorphic computing. So we had a question on this also, a forecasting question on this that we released. And this, this is very AI centric and neural network centric. So what it tries to do is to emulate the neural structure of the brain. And Intel is one of the leaders in this, but certainly not the only company that is involved. One of the promises of this paradigm is that it takes a lot less energy but it's specific to neural network kind of training and neural training, but it does take a lot less energy, and I really mean a lot less energy, orders of magnitude less energy than GPUs and even TPUs. So again, like you can imagine that if this can scale up, right now it's only available to research community, but if this can scale up and it becomes commercially available, we are suddenly, training a trillion parameter model might become as easy as what would now be training a million parameter model on a laptop, right? So I can imagine that if this becomes available, I would just buy this. It would, like all technology, the price would come to a point where most people would be able to buy it. And just like a GPU, you put it in your machine and suddenly you're able to train trillion parameter models. So if that happens, this is again only open to research right now. So just like quantum computing, right? But we're not at the stage yet where this can get integrated into normal PCs and laptops. And finally, last but not least, the domain-specific architectures are also being heavily investigated. So by domain specific, this is a call from IARPA. It's closed now. They've even announced the results of who won. But this came out, sort of last year, where IARPA solicited proposals along with the Army Research Office for advanced, sort of architectures that 10 years from now, that was the time frame they were looking at really, we would get advanced, architectures for doing what they call graphic intelligence. So this is like working with graphs, like a social network would be a very good example. But also, graphs could be all kinds of things, money flows can be modeled as graphs, cybersecurity has a very close connection to graphs. So IARPA seeks the research and development of innovative, energy efficient, reliable computer architectures to implement large-scale data analytic applications. And the key computational problem is that today's computers were designed to address yesterday's compute-intensive problems rather than today's data-intensive problems. So these are 3 examples that I've given you. To my knowledge, there aren't any more. I mean, it's these 3 that are dominant: domain-specific architectures, which is kind of looks at specific domains and is not really all that generalizable to other domains. But the domain is important enough that we care about this domain-specific architecture, especially for the intelligence community. The neuromorphic computing, which would be applicable to almost any neural network if it's commercialized, and quantum computing, which is even broader. And for that reason, perhaps, is really a point of contention right now. So I will stop here. I mean, I do have, some 2 other slides where these are 2 books if you're interested, but they are on knowledge graphs and which is kind of my area of research and is intimately connected with AGI. I have a new book coming out this year on AI and industries of the future. So if you're interested, I can definitely, just watch out for that. It should be out sometime this year. And you can connect with me on LinkedIn. I usually connect on LinkedIn. I'm not very active on the other social media. And otherwise, do stay in touch. But I will just stop here. I know I'm a little bit delayed, 3 minutes more delayed than I should be with the talk. But let me just stop at this slide and switch away from full screen. But I want to leave you with this slide as a summary, which is that, Moore's law, right, is not dead yet, but the models are becoming larger and more energy intensive. Even if the Moore's law is not dead yet, and it's just not, we can't really run AI models cost effectively on chips that follow Moore's law. And these larger models, people argue about whether we need the large models. Why can't a small model do what the large model is doing? And these are all interesting academic questions. I mean, I have a vested interest in those questions as well. But when we look at the empirical evidence, the reality on the ground so far is that larger models have proven more effective against smaller models. And companies are not stupid. They are going into this and spending many millions of dollars because they have seen that larger models are more effective. And both Chinese and US big tech are invested in making them even bigger. Future of computing should not just be faster. It also has to be more energy intensive. And it has to be more data intensive rather than compute intensive. There are many things we don't know, but there's a lot we do know. I've pointed out some sources in all the slides that will hopefully help us forecast what we don't know. And of course, to this audience, forecasting effectively, as you know, right, really helps communicate to the lawmakers on where they should be to fund more research, right, to develop, these benchmarks like ML Perf and these language model benchmarks and so on are really they're not for free, right? They do take a lot of energy and time to actually build these benchmarks, to get people to use these benchmarks. And, typically takes a consortium, academics and industry partners have to be involved. And typically without government support, it's very difficult to bring everyone to the same table, a lot of times. So, I think that the forecast could really help convince, policymakers that this is something they should be looking at. And if they don't, then we would fall behind in the race. So with that, I will stop and leave some time for questions.
Thank you so much. I see we've already got one question in the chat, so feel free to keep them coming, but we'll start with this one. Alex is asking, or saying that the chinchilla results earlier this year from DeepMind indicate that the real constraint to further advances is data rather than model size or compute. And do you have any comments on what we can expect on that front? And if you could also give some background on Chinchilla for everyone in the audience, that would be great.
Yeah, so I haven't looked at it for a while now, I'll be honest, but I'll tell you what the argument is over there. And it's not just Chinchilla, but also Andrew Ng, who is one of the pioneers in some, back in the day, he was the one who invented the topic model and was, I think, head of AI research or very prominent in Baidu at one point, and professor at Stanford and so on. So it's a very, well-respected guy in AI. And what that camp is saying, I mean, without denying the effectiveness of deep learning, what they are really saying is that, which is an old argument in some ways, is that, we as humans are, we're not really processing, we're not reading the whole of Wikipedia and the whole of the web and processing the whole of Wikipedia and the whole of the web in our brains to understand language. For example, again, I'll use language understanding as the example. But yet that is what these large models need to do. So the models are big, and in order to train the parameters more effectively, they also need a lot of data. And the argument there is that what we need instead is that we need to work with smaller data sets and learn more effectively from smaller data sets. If that is the case, then the question becomes that is the smaller data set, does a smaller data set necessarily imply a smaller model, right? And there's some evidence that that's not really the case. One example would be the switch transformer that Google came out with last year, I believe, or it may have been earlier this year, which is a very sparse model. So unlike a lot of these neural networks that are here now, the switch transformer is a new kind of transformer that can support more than 1 trillion parameters because it's sparse. And for a sparse model, one might argue that it would be able to learn more effectively from smaller data sets. But I haven't seen a compelling argument yet that small data implies less computation. If you think about it, it could be that you are getting a smaller data set or you're being more data intensive, but you still need to do many iterations over that data set, or you still need to do a lot of compute over that data set to actually learn a good model. So it's still a controversial hypothesis whether we can actually have lower compute theoretically and still get the same performance. And this is why people are so focused on energy intensive computation as opposed to, because the truth is that we can go for smaller data sets as an academic exercise, but the Chinese have a lot of have big data available to them, and they are using it. Now the payment systems, the surveillance systems, they're all connected. They're all being used by some of the computer vision companies over there. It's a little bit dystopian, but they are using much bigger data sets. So the main players are not shying away from using bigger and bigger data sets and bigger models. So this result is interesting, but it's one result, and it's for one very specific problem, and it's not clear that it's generalizable. So we need to see more on whether we can make do with small data and whether small data implies smaller models. So those are two separate related questions. We don't know the answers yet to that. So far, the bigger models have proven very difficult to beat. The state of the art is still the bigger models. And by the way, speaking of DeepMind, one should note that their models take millions of dollars to train. So, they can claim these things, but when you look at AlphaZero and the models that have become very prominent, they took millions of dollars to train. They even made a loss for Google. I don't know if that's the case now, but back when they were first acquired, for at least the first couple of years, they were, if you look at the accounting, they spent so much money training their models that they were making $1 million losses for Google, which it could absorb. But that kind of reinforces the point I'm trying to make, right? That we do need energy intensive chips that don't take millions of dollars to train. And I don't think DeepMind has claimed yet that it's actually trained the system in a cost-effective way. So it's an interesting question. But what I'm trying to say is that there are certain implications there that don't necessarily apply. We don't know if it's cost effective. We don't know if it's if less data means less compute. We don't know if less data really will beat the bigger models and the bigger data on all kinds of other problems that Chinchilla has not been applied to. So, but definitely a space to follow. Yeah.
Great. Thank you so much for that. We do have another question from Gabriella. She's saying that in terms of the current prioritization, it seems that a lot of the focus on advanced computing have energy constraints as a lower priority compared to others. And how do you propose perhaps bringing the topic of energy constraints higher up in the ladder of priorities, and your general thoughts on that?
It's a great question. Yeah, you're absolutely right. I think that before, interestingly enough, it took something like climate change before the community even started talking about the energy intensive natures of traditional advanced computing. So I think the future of computing, which I'm not referring to as advanced computing because it's still kind of the future of computing, it's not really there yet. These do tend to be very, certainly neuromorphic and domain-specific architectures, arguably are much less energy intensive, and they do put energy front and center. So you can see here that the three requirements here are, the innovative, of course. If you're writing a proposal, it has to be innovative, so we can ignore this word. But the two requirements that the DoD stated was certainly energy efficient and reliable. It went without saying that the input would be large scale and data analytic, but for this, specifically for large scale data analytic applications, we wanted energy efficient, reliable architectures. Reliable is important because not every architecture might be reliable. The early quantum architectures were not reliable, and it turns out that as the traditional advanced computing, as they start using more and more power, they might start becoming less reliable. I'm not an expert on that, but I've read some work that the design changes. There are some real things you have to consider as you start fitting more and more and more chips very densely into or more and more transistors very densely into a chip. Reliability problems start to occur. So I think that how can we move it up the ladder of priorities? My view really is that we need to bring up, this administration is very interested in climate change, right? And I think that that's the angle through which we need to bring up the energy as a priority. So, I read a paper the other day, or read some blog the other day where it turned out that to train even this BERT model, which is really not all that big, right? So this model here, which is a very, it's a great model, it occupies a very important position in this curve, but it still takes, if you, in the early days, before optimization, when and I say early days, it's like 2018, so that's how fast the field moves. It would take the equivalent of one house. So the energy that it takes one house in a year, that's how much energy it took to train this model once. And typically you can't train it once, you have to train it several times, because in machine learning, you have this thing called hyperparameters, where it's kind of like you have to try several times before you basically hit the right model. And so, basically you could end up, taking the amount of energy that it would take like a village over or even a small city over an entire year to like train one of these models effectively. And speaking about neuromorphic computing, so I think there are a number of really good resources. Unfortunately, I am not seeing as much as I would like to on this, maybe because there are fewer companies involved. Intel is one, IBM is one. I think Qualcomm might be one of them, and I think there's a smaller company other than that, but really not too many companies. HP is another one, but we don't have the Google and Facebook and Microsoft, to my knowledge, investing in neuromorphic computing. I think some of them are more interested in quantum computing, and the others are, building their own chips using, for example, TPUs. They believe that, if they build something like a TPU, at least in the short run, in the next 3 to 5 years, it will get them to where it needs to go. Eventually, I think they will run into a problem, and maybe they are thinking that at that point it will become more parallel, or to Alex's point, maybe we will have smaller models. Maybe it would be that we do have smaller models that are more data intensive, or maybe quantum computers become available by then. Certainly Microsoft and Google are investing in that, right, as is IBM. But we're not seeing as much on neuromorphic as we would like to, but credit to Intel that it's still pushing on this. I highly recommend this article here. This is a 2022 article. I think if you just search for neuromorphic computing, 2022 Nature Computational Intelligence, you will see it. It will come up immediately, I think. This is a very interesting and kind of long article, but it's very accessible. And it goes into examples of neuromorphic chips and why neuromorphic. And I think this is the article that you want to, this is the one I recommend. It's not speculative because it has been published in a very good journal. And I think that if you read this article, it also has many citations inside it. So you can, then you would go from that to the references, right, that it's citing. The only other thing that I can recommend beyond this is the Intel's neuromorphic research community, the INRC. And we have a forecasting question on this, but I think we point to some of those resources as well. So, if you're interested in this, do check out that question and the resources in that question. But yeah, if I had to point to one a really reliable resource to learn more and to kind of, just learn a lot about this, it would be this article over here. Yeah.
Great, thank you for sharing that. I'll make sure to include that resource to the pros for anyone that's interested. One question that I had for you from a broader perspective, just really quick before we all sign off, is if in 50 years, looking back, AGI, we can definitively state, was never reached, what do you think would have been the main bottleneck or the main reason? Would it have been that there weren't sufficient advances in model design, data compute? What do you think would have been the biggest hurdle that was not reached?
It's a great question. I think that I hate to say this, but I think I almost, if it wasn't reached, then it's because some breakthrough in AI that we were hoping for was not reached. And I think the reason why that breakthrough was not reached may be because, the AI community has gone through many winters in its time. For example, something like neural networks have been proposed, 40 years ago, actually, and even before then. The first paper that was very influential and that talked about what is now a very fundamental unit in a neural network, which is called a perceptron, was by Rosenblatt in 1969, I think. So what he showed was actually a negative result. He showed that a perceptron could not do certain computations, and that was followed by a winter. No one worked on neural networks for a very long time. The 1980s were an era of expert systems, rule-based systems, logic, and so on. But then neural networks picked up again in the 90s. They were again very popular. A lot of people thought they were on the cusp. Then again, they kind of fell by the wayside, and other models, started taking over. For a while, there was a lot of progress on other models. And the OG of neural network, one of the OGs, Jan LeCun is another one, but Jeff Hinton was one of the OGs and won the Turing Prize along with Jan LeCun and I think one other person, Joshua Bengio. And Hinton, to his credit, didn't give up, right? He worked on the ImageNet data set and it came out in early 2010s, showing that the deep neural network, that this was the neural network with more layers that we now take for granted almost, but back in the day, it used to be like, they didn't used to be deep. They used to be like tall, but not deep. And mathematically, it turns out they are very similar, but practically, they're not that similar. It's easier with more computation and data to train the deep neural networks. They may have certain other advantages that we are just coming to discover. But he tried, and then at that point, right, when he showed the result, obviously people replicated it, and that was like a, like if you read the theory of scientific revolution, it's not linear, right? It's like stepwise. The way that science and technology tend to advance is that it's like stepwise function. So the success of these new era of deep networks was really like a step. And so we are looking for that next step, right? What's going to be the next step? And the danger is that if we keep working on deep learning, it will be more linear, then stepwise, we might think we are getting closer to AGI, but in reality, we would just become better and better and better at certain problems and not solve a fundamental problem that needs to be solved to get AGI. Now, some people are claiming neural networks will get us there. Others are claiming that no, something more is needed along with the neural network, something more fundamental that could work with the neural network. It doesn't have to supersede it, but the neural network itself is not enough. So all of these debates are going on. And so to summarize, it could be that 50 years from now, we are too focused on improving what we already know, which are the neural networks, and creating bigger and bigger networks, than on the fundamental advance. And the social and the social landscape has changed so much that we basically have to work on neural networks to get any funding and to get any traction, and no one is interested in any other ideas. And so it's kind of like the new idea will never have a chance to have the same journey as the neural network did, right? The 30, 40 year, 50-year journey. I mean, if Rosenblatt had not published his paper, and if after that, if others had not published their papers and tried things that didn't work, and then the right time, at the right time, and with the right resources, it did work. But it didn't work in a day, right? No one invented it in a day. They had researched it for a very long time. And the folks who had researched it as young researchers, as older researchers, they recognized that the time was right. They didn't give up on it. I fear that the younger, my generation is so obsessed about deep learning that they are not looking at new ideas, so that when the right time comes for the new idea, we won't have the new idea. We will still be in this neural network landscape. And if the first camp is wrong and neural network is not the way to achieve complete AGI, then we would not achieve it in 50 years. If they're right, we would, right? So we would have the neural networks with some things, and then we would get AGI. But if they're wrong and something more fundamental is needed, we're not investing in those other things as much as we are investing in neural networks by a long shot. So that's what could go wrong. So we need more diverse research. I think we need to start diversifying. There are calls for that, but it's kind of like there are calls for it, but like 90-95% still is very neurally focused. Yeah.
Right, that makes sense. All right. Well, thank you so much for answering that question, and thank you for presenting and taking an hour out of your day to present for the pros. And to the pros, thank you so much for attending and for your thoughtful questions. I hope you enjoyed it, and I hope you all have a great week. Just a note that, of course, tomorrow is the last day of the month. So if any of you pros do need to get forecasts in, do make sure to do that. But thank you again, Mayank, pros. Have a great one.
All right. Thanks. Have a good one, everyone.